I'm very pleased to be here today to introduce you to the second day of our first International Spring School. The topic of today is the valorization of byproduct, and in particular we have what role does CleanTech play in extracting value from byproducts, an overview of the state of research and new products. So I'm going to be very, very quick on the introduction, don't worry. And then we are going to go into this topic a little bit deeper. The first part will be a state of research. Then we are going to have a 30-minute break. And we are going to jump to the second part, the innovative products. So it will be pitches from companies. And we will end this morning with a 15-minute session of poster pitches. So when we valorize byproduct, what's very important, of course, is the value. The value we can have by extracting byproducts. And we can have good value, but what's important as well is to keep sustainability in mind, always. That's why we wanted to put these topics today. The CleanTech can play a huge role. My name is Cécile. I work for Wagralim since 3 years. I arrived with the circular Walloon strategy, which started in 2021. So it was the first circular strategy. This strategy focused on different value chain. One of it is the food, and Wagralim was in charge of developing the circularity in the food sector. We worked on different topics of circularity. We work on packaging, we work on water. We also work on developing new value chains, like new vegetable proteins. And we also work, of course, on byproducts. Byproducts, we have a lot of different projects by Wagralim. We have a regional project via the strategy. We have also a cluster project, but we also have a European project that we are going to develop in the second part of today's session morning. So let's start with our first speaker, Hélène. Hélène de Wever holds a PhD in applied biological sciences. Since 2001, she worked at VITO, so the Flemish Institute for Technological Research. She leads the processes and biomass processing team, and she has over 15 years of experience in bioprocess intensification and CO2 valorization. She's currently also leading the IBISBA project linked to the European Research Infrastructure Initiative, IBISBA. So the floor is yours.
Is there a pointer or anything?
I'm going to check. If you want to start, just in case. Yeah, okay.
Okay, thank you for the kind introduction and also for the invitation to come and speak at this spring school. Good morning, everybody. I want to start with a few words on VITO, because maybe not all of you know exactly our research institute. We are a science to technology partner, both for the authorities, for society, and for industry, and we try to convert scientific insights into technological innovations. We are active in 3 impact domains, which you will see here. The first one is regenerative economy, with a lot of links to circular economy, bio-based economy, closing loops. A second impact domain is healthy environment, where we want to make the link in between what is happening in terms of release of compounds into the environment, both on ecotoxicity and on human toxicity, if I may say like that. A third aspect or impact domain is resilient ecosystems, and there we are active in climate mitigation approaches and also climate adaptation. And of course, more and more also resilience, availability of infrastructure, access to resources, and so on, in the current context of security and so on. To give a few numbers, we have about 1,300 scientific experts in our organization, revenues of about 270 million euros per year. And you see, of course, that we have a number of key performance indicators in terms of output, scientific publications, but also spin-offs and patent applications. We also have PhDs and postdocs and vacancies available, so if that is of interest to any of you, please have a look. In my team, we are focusing on two different topics, and the first one is on biorefinery. And so I will try to make the link between that one and biotechnological processes and how they integrate together into concepts to valorize waste streams. On the left hand, you see the type of biomass streams that we've been focusing on in the past and also at the moment. That's microalgae, it's macroalgae, it's insect biomass, but also a variety of wet biomasses and side streams. And then through a plug and play with a variety of unit processes, we try to get out the main fractions of those biomasses. And you see then the major ones, polysaccharides, example chitin, lipids, but also minor compounds that have a higher added value like colorants and antioxidants. And then you see on the right side the kind of applications or sectors that this can be relevant for. For today, agro-feed and food is maybe the most relevant one, but we also go to cosmetics and health applications. In terms of biorefinery approaches, I want to start with two different concepts. So if we look into wet biomass streams coming from food and other types, you can go for the direct biorefinery approach, but then you have a very, let's say, biomass with a complex composition that can vary over time and also between the different fractions which are there. So rather than going for the direct approach, it can also be of interest to take an indirect approach and to convert this heterogeneous biomass into a more homogenized type of biomass. And that's the approach that we took by inserting this insect cultivation step in such a biorefinery. So that means that the left side, with the green fractions that you can get out of biomass streams, like proteins, carbohydrates, and minor compounds, you can actually convert it into an insect biomass in which other types of compounds enrich and can be recovered. So this is in focus of sustainable chemistry and sustainable new value chains of interest. Because you see that insect biomasses then are enriched in lipids or fats and chitin and chitosan. And both have quite a lot of interesting applications for a variety of sectors. So if we look into chitin and chitosan, what is this exactly? So chitin is a polymer of N-acetylglucosamine units, and depending on the degree of acetylation, it's chitin or it's chitosan. So if we remove or deacetylate, we convert chitin into chitosan, we can further depolymerize the polymer and then even functionalize or derivatize the fragments that we obtain to get a whole range of derivatives. What are the applications of all these intermediate products or target products? Well, you see them there on the screen. It can be biopolymer building blocks as such. They can also have antimicrobial, anti-cholesterol properties, and a lot more. And they can be used in formulations for a whole range of applications, both in agriculture and in food industry. And to name a few, this can be slow-release coatings or encapsulations, but also biodegradable films and coatings in post-harvest applications. So what if we want to look into such insect biomass and get the chitin and chitosan out of there? So we've done that for a number of years in the framework of an innovation mandate that was running at our institute, where we started from the insect biomass and generated a whole range of chitosan samples. You can imagine that you can produce them or that they can have different molecular weights and different degrees of deacetylation. And these two properties actually determine also what their characteristics are and for which applications they may be relevant. So that's why we produced a whole range of these products, tried to investigate also how reproducible the processes and the product composition was, and then linked that to a whole range of bioactivity properties. And then we selected a number of these samples to also apply and investigate and assess them for biostimulant and edible coating applications. I will come back to that later in the presentation when I made the link also to enzymatic conversions. We also looked into the use of this insect biomass for pet food application, and that's a strategic basic research project that is ongoing still. And that looks into how can we valorize these kind of biomasses and not only the chitin, chitosan present in there, but also everything else, because we always want to reach as much as possible full valorization of biomass for the particular needs of pet food. And to also give you an indication of the scale of work that is being done, you see there that it's really 100 kilograms of material that is being processed, either as wet fractions or as dried fractions. And from there, chitin is extracted and derivatized, but also the other fractions are being generated, which means that we had a whole range of 300 gram, 30 gram fractions that could be investigated in detail for their analytic composition, so lipids, proteins, chitins, but that could also be evaluated in vitro for digestibility testing, composition in terms of amino acids, and also antimicrobial and prebiotic effects. What does it look like? You see on the left side the kind of insect streams that we get. Then we go, for instance, to an extraction phase. This can be with green solvents. This can also be aqueous. Some centrifugation steps, a number of other technologies that are being applied. And then you see the variety of products, crude extracts, that can be obtained from there. So including both proteins, lipids, and chitin, chitosan. Of course, starting from insect biomass can bring some issues in terms of safety. If you start from waste streams, it can also have some maybe allergenic effects, so it cannot be applied for all potential applications. So we're also looking for other types of side streams that may be rich in chitin or chitosan. And actually, in the past years, we've had 2 projects that ran on fungi side streams. And so this was in particular mushrooms, where the little stems from the mushrooms are not harvested, if I may call it like that, and are normally being thrown away, but they could be an interesting source also of material that can be extracted from them. And again, there we were looking into ways to fully valorize the biomass of such mushroom stems, if I may call them, and to see how they can be used in food applications. So that was beyond the chitin chitosan fraction alone, but also considering the proteins and sugars in there. These were a few high-level indications on a type of biorefinery approaches that we can take. We also need some conversion steps potentially in there to give additional functionality to some of the fractions that are obtained. And then biotechnology very often comes in. So what we do in our team is actually summarized in the scheme here. So we have either enzymatic conversions or whole cell fermentations, and we convert a variety of feedstocks into a whole range of target products. In terms of feedstocks, this is either more organic type of feedstocks, and then the ones that interest us most are polysaccharides, carbohydrates, for instance, the chitin chitosan. It's also lignin precursors, that's then from another type of second-generation feedstock, so more the lignocellulosic ones, wheat straw hydrolysates, and so on, but also oils and fatty acids and how these can be further valorized. And also with new crops being grown, I think we have access also to new types of these materials to valorize them. We also look into the C1 platform, so quite a lot of activity in CO2 as a side stream and feedstock to convert into a variety of products. That's not the topic of today. If that interests you, we can discuss later on as well. And then you see on the right-hand side the type of products. Fuels is a bit commodity, low value. Biopolymers, chemicals a bit higher, but we go all the way to cosmetics, nutraceuticals, and additives, prebiotics, and the more. Our biggest interest in bioprocess development and optimization is actually going towards process intensification, so getting the most out of what we put in. Typically what we do is we have a bioprocess. At the end we collect whatever is there, and then we do downstream processing through a combination of separation, extraction, purification steps. But actually we like to integrate also separation with the bioprocess itself. So that brings, let's say, added features to this hybrid concept, where we can improve mass transfer, increase cell densities, remove inhibitory products, shift reaction equilibria, and so on. And so these are the kind of things that we want to debottleneck in bioprocess development. So let me take a few examples on enzymatic conversion, and then particularly focusing on tailored hydrolysis of polymers. For today, I take the example of carbohydrates. Of course, for proteins, this could be applied as well. The idea is there that we want to obtain oligosaccharides in this particular case that have a dedicated degree of polymerization. And so how many monomers do we actually have in the oligo? And that is something that we want to refine and tailor as much as possible. What is the interest in oligosaccharides? You see a whole range of them, and also a whole range of starting materials that can be considered and that we have also been studying. So you can start from pectin, that gives you pectyl oligosaccharides. From chitin, you have chito-oligosaccharides. From mannan, it's mono-oligosaccharides. So there is a whole range of them. And the interest is the properties that these kind of oligosaccharides may have. So depending on the source that we start from and the type of composition, they may have prebiotic, antioxidant, antimicrobial properties, but can also be used as plant elicitors or plant biostimulants. So we have actually looked into that, and the way we have investigated these processes is first the conventional way. You do the batch enzymatic conversion. Depending on how much the batch takes, you will have a more pronounced or progressed level of depolymerization. And if you take it too long, you go all the way to the monosaccharides. That's not what interests us. So we have to end somewhere at the time point where you have sufficient oligosaccharides, but not too much of the monosaccharides. Because the monosaccharides inhibit the enzyme and also may have negative impacts on prebiotic properties. At the end, we need to inactivate the enzyme because it's there in the mix with the target products that we have. This may lead to allergenic and color effects that are not so desirable, but okay, that's what it is. Then you kind of do a first separation of the enzymes, and then you may have a membrane cascade with increasing molecular weight cutoff to target the recovery or the collection of certain degrees of polymerization of your oligosaccharides. Then you can collect all these different fractions and do the bioactivity assays on them. Another approach is that we go to a more continuous way of processing. We couple a membrane to the reactor in which the conversion takes place. We continuously feed the feedstock and we continuously harvest the oligosaccharides. So by balancing that system, you can actually separate the enzyme, which is retained in the bioreactor system. You have the oligosaccharides in your outgoing stream at the permeate of the membrane, and actually you can reuse and keep on using the enzymes in a continuous process, which typically increases the productivity. Of course, it comes with an extra cost if you have to implement that, and there may be also issues of membrane fouling to be considered. Decreasing enzyme inhibition as well, because the monosaccharides are not there in high concentrations. So we have, for instance, applied that for the hydrolysis of pectin as a starting material. This can be obtained from onion hulls, from pumpkins, from sugar beet pulp. So these are renewable feedstocks in which this pectin is present. We extract the pectin from it. We apply commercially available enzyme mixtures on that, and then we go for the enzymatic hydrolysis, collect a number of fractions, and do the bioactivity assays on them. In this particular case, we were focusing on prebiotic properties. As an example of what it looks like, you see here a graph that shows the progression over time during continuous operation, where we have, with the green triangles, if I may say like that, I don't have a pointer here, the green triangles indicating that we are reaching a steady state operation in the continuous mode, and that about 80% of the material that we have is present in the form of oligosaccharides as we want it. The composition is constant over time, with this, the constant ratio between arabinose in this case and the galluronic acid, similar to what is present also in the original pectin material. You see a number of parameters which are quite good in terms of volumetric productivity and specific productivity, and also the prebiotic effects could be demonstrated both on lactobacilli and on bifidobacterium. So positive effects also on the fractions that we could produce like that. A second example, and that links back to what I was telling in the first part on the biorefinery approach, links then to hydrolysis of chitosan. So here it's the same thing. We can start from materials that we have produced or extracted ourselves, or we buy commercially available chitin or chitosan. Then we, from a variety of sources, we again apply commercially available enzyme mixtures, do the enzymatic hydrolysis, and in this case we looked in a whole array of functionalities, antifungal activity, plant elicitor properties, and edible coating applications. So coming back to the biorefinery approach, we start, for instance, from insects, we go to a pulp, we further extract certain fractions to go to a residue, and from there we obtain chitosan. You see that the level of chitin and or chitosan increases over time, the concentration present in the fractions that we collect. The last step is then the enzymatic depolymerization, And there we can go to high molecular weight, medium or low molecular weight, or even all the way to the chitin oligosaccharides. So that's then, let's say, a few monomers that are linked to each other. You see also the type of materials that we then obtain and what they look like, and then we go into a bit of the application testing. So on the left side, you see that we assess the material for film forming properties, which were confirmed. And this is then important because we want to use it for edible coating applications or other applications where film formation capacity is important. And then on the right-hand side, you see the biostimulant properties, with at the left side, the material that was supplied there, and on the right side, the reference cultivation. Also, plant trials were performed afterwards, but for those I cannot share the results. We also apply the same kind of process intensification approaches on fermentation processes. I will only give one example, which has some links to the food sector, which is a lactate production, or to biopolymer, bioplastics production, PLA. And here we started from second generation feedstock, so C5, C6 sugars that had to be converted, as in wheat straw hydrolysates. The whole idea there is always lactate fermentation already exists, starts from first generation sugar. What if we shift to second generation, and how can we intensify it? So in collaboration with companies, we had some targets to meet, and they defined also what the industrial relevant conditions would be, even for the lab scale testing. So we coupled membranes to the fermentation, we go to continuous operation, we achieve high cell densities, and the idea is then first doing optimization on first generation and then on second generation feedstocks. What we achieved were the same lactate titers as in the reference process, so 100 grams per liter, productivities which were 5 times higher than in simple continuous mode, 10 times higher than in batch operation, reaching 30 grams per liter per hour, which was a very, let's say, challenging target, which we did meet also on second generation feedstock. So I think these were really very nice results. Sterility maintained, because very often that's a bit of a hurdle for industry to shift to continuous operation or even high cell density ones. Can we maintain sterility or axonicity over time? Yes, we did that for a number of weeks without any issues. Of course, there is membranes involved, potential precipitations that can occur, scaling and fouling. This is a point of attention in case we want to scale this up, on how that will have to be kept under control. A second example here is on conversion of organic waste streams, biomass type, wet biomasses, food waste and so on, that we have investigated towards the production of carboxylate, so a mixture of volatile fatty acids, acetate, propionate, butyrate, which have a very broad range of applications, as shown here on the right side, towards biopolymers, medium-chain fatty acids, esters, alcohol. So a very nice, I think, platform also for the bio-based economy and for setting up new value chains from food waste, for instance. In this particular case, we again wanted to avoid the inhibition effects of the acids that are being produced in fermentation by coupling it to electrodialysis. I will not go into the details of electrodialysis. That will be done by the next speaker, as I saw. So you will explain the basics. What we tried to do here is come up with a very innovative concept at the level of the stack design of the electrodialysis that allowed us to combine a number of functions in one. So on the one hand, we removed the acid from the fermentation to avoid the inhibition effect. At the same time, we brought in base into the fermentation to control the pH, and that we did without actually removing any cations, which often happens at the same time. So a number of functions that could be combined, pushing the productivity by 50%. So possible trajectories that we can offer as Vito, or that we can jointly develop together with you, is in terms of biomass processing, where we can generate up to kilogram samples of material for application testing. In biotechnological process development and optimization, where we can look into the bottlenecks and provide solutions for that, do some supporting modeling work, and also support further scale-up. So a whole range of technologies available to plug and play and design the best biorefinery process. The type of equipment that we have, giving you an impression on the scale for the biorefinery work and for the biotechnology and fermentation work. So never standalone fermenters, but always complemented with a lot of extra separation technology features and online measurement and control. Then I have a last item to address, where I still have sufficient time, I see, and that's on a completely different level. This is about a research infrastructure initiative that is actually under full development at the European scale, and where we also want to make the link as Belgium to that international initiative, and it's called IBISBA. So IBISBA is, as I said, a European Research Infrastructure Initiative. It's a distributed research infrastructure, so the idea is not to have all the infrastructure present at one single location, but it's actually a number of good research institutes and universities all across Europe that join forces to bring together all the relevant equipment and expertise that is needed in synthetic biology and industrial biotechnology, including the upscaling, and to offer that in an open access mode to both academic and industrial parties. So this is then through certain procedures that it goes, so it's present on a European roadmap for, let's say, research infrastructures that are considered very important and crucial for Europe, and so this is being recognized by the European Union. And actually the kind of configuration that this refers to is a kind of business alliance between all these academic organizations to offer these services to other users. We are already active in the European research infrastructure landscape, so a number of European funded projects are already ongoing, and you will see more and more in the new European calls for proposals that IBISBA is explicitly mentioned and is also proposed as a partner, a preferred partner for the consortia that are being developed there. So I think it's really in the picture at European level. What does it offer? You see on the right-hand side a summary in 5 big domains of science and technology that are a bit cross-cutting and complementary. So you see first protein discovery and engineering, so that's at the level of enzymes. Then we have production strain development, and so there it's really microorganisms. Bioprocess development and optimization. Omics and analytics is also a very strong one. And then the supporting techno-economic assessment and life cycle assessment, which is also included there. Then on the left-hand side, you see the links that are being made to a variety of sectors. So that includes energy and environment, chemicals and materials, digital and biomanufacturing, but also food and health is taking up an important place there. What does the current research community look like? So you see here the logos of all the entities that have currently signed a memorandum of understanding, and that have, by doing so, really commit to helping put IBISBA on the European level as a legal entity, because that's actually what we are working on for the time being. And the idea is that in 1 or 2 years from now, this will actually also be achieved. For Belgium, at this moment, only Vito has signed a memorandum of understanding, but by doing so, we've also taken the initiative, because that's the way these kind of European research infrastructures are being conceived, is that actually every country has to set up a national node that links to the European legal entity. And so there, Vito has taken the initiative to coordinate this in Belgium. But actually, because we have the regions in our country, I have to go through a region, and we've actually done then an application through the Foundation for Scientific Research, FWO, for the application, which is then called IBISBA Flanders. So that's the route that we have to take. We've done that in collaboration with a number of academic institutes, so the Free University of Brussels, Catholic University of Leuven, 2 entities of Ghent University, and the Flemish Institute for Biotechnology. So that's the consortium that we have brought together to launch this initiative. In a nutshell, what do we want to achieve? We want to set up new value chains from locally available resources. So it's really about all these second-generation feedstocks, waste streams, side streams that we have, and how we can bring value to those. It's a research infrastructure project, so again, it's about setting up equipment and infrastructure that we make available, so it's not research itself. And for that, we have to apply for additional research projects or set up bilateral collaborations, for instance, with industry. And our focus is to have an infrastructure pipeline that targets production of biomaterials and chemicals. We focus on non-conventional microbes, so not the typical Saccharomyces cerevisiae or Escherichia coli, because they are well known already and a lot is happening there. But we think that to take full value of a variety of feedstocks, we actually need these non-conventional microbes as well, and there is still a lot of developments to do. So ideally, we want to come to the Flemish process-integrated biofoundry with unique capabilities across temperature ranges. So we go up to thermophilic temperature ranges and also across scales, so from very small scale to pilot level. With, of course, all the contributions this can bring to increased competitiveness, social advantages, and strategic autonomy. And I want to end then with an invitation to the Wallonian experts in this domain. And this is not limited to Flanders. Collaborations are possible with the other regions in Belgium. The thing is that this actually goes through funding then via the Walloon region. It cannot be funding from FWO, but we can, of course, make one joint IBISBA Belgium node. I said that's the idea. So if there is an interest for that, we are more than happy to discuss. And then we have to explore how that can be realized, of course, through funding also from the Walloon authorities or funding agencies. I don't know what the procedures are here, but I think you are probably better placed than me to do that. But so an open invitation to discuss this and for the years to come to expand also with your expertise in this initiative. So with that, I end with a number of acknowledgements on the work I have shown and on the team that has been involved, and I will end here my presentation. Thank you.
Is there any question now for Elaine, for the organization, what they do? Because there are a lot of different projects, and also about IBISBA maybe. Yeah.
Thank you, Elaine.
I'm going to bring the mic.
One? Yeah. Just a question about the IBISBA. What is your philosophy of the access to the platforms, to the researchers versus industrial partners? How do you see this?
So the choice of the legal entity defines how that is going to be organized, and we are currently writing statutes, rules of operation, and so on, in which, of course, all these different institutes have to agree on the way that it's going to go. Typically, with the legal entity that we are currently aiming for, there is a limit to the, let's say, the bilateral work with industry that can be done, and let's say the profit that can be obtained from such collaborations. But the maximum, I think, would be 20% of revenues that come through such channels, and 80% have to go through publicly funded or academic collaborations. The thing is a bit, there is a variety of accesses possible, so some things are really very concrete and routine, maybe almost analysis that can be very clearly defined, this is what it is. But what interests us most is to have collaborative research projects in which we do joint developments with other parties. And then that will go through, I don't know, European-funded collaborations or bilateral or PhDs, or so a whole range of things is possible. Because it's going, or because it is on this roadmap, Europe also has a lot of dedicated research infrastructure calls, so they are only meant for this kind of research infrastructures, and these offer also the opportunity for so-called transnational access projects. So what that means, and we have already tried that also in previous funded European projects, is that a company or a PhD student or a university from country 1 requests access to equipment in country 2, and maybe for another part of the work in country 3. So it cannot be in country 1, it has to be in a different one. So, and these kind of constellations are possible. Usually for this kind of approach, there is funding available. So it's really applying then for the transnational access funding, and therefore there is then a number of procedures and application procedures that are also defined and described. And these calls are then launched with a certain frequency during the lifetime of such research infrastructures. So it's very broad and flexible in the type of collaborations. At some point, even industries can become part and member And so it's not excluded that this is only academic entities that step into the consortia.
Which does make sense when we think about the scaling up.
Yeah.
Yeah.
And so scaling up pilot plants are also currently already in, let's say, the number of groups that I showed on the summary slide. So they're already there, but since there is so much different expertise and technologies there, there is space for many more. So the more countries that can join, the better, because then we cover a lot more expertise. But it's now about getting the legal entity in place and then having everything else organized, also contractually and so on.
Thanks.
It's a long answer to your question.
Yeah, that's okay, thanks.
Any other question?
Okay, thank you so much. That was a very, very good, very fascinating presentation. My question is about economic viability, so it's more about the biorefinery sort of part. To explain, I've been working in a project a few years back. It was about crustaceans, so shellfish waste refining. You take out astaxanthin, you take out chitin, chitosan, calcium, and whatever else, and only for the company then to conclude that it's actually not financially viable. So what is your opinion or experience sort of in the space? Where are we, or do we need subventions, or, you know, kind of to make it really work?
Yeah, fully agree on that. So in all of the projects that we have, of course, also this techno-economic assessment is included. Life cycle assessment as well, because one thing is, do we get really sustainable processes as an alternative for what we have? So that could be one benefit independent of the techno-economic assessment. But the techno-economic assessment, I think, usually only makes sense when we have full valorization of the biomass, not just one fraction there. And we need to have a high added value product amongst it as well, because otherwise it's a very difficult case. And I think at this moment, that's unfortunately the case for a lot of the bio-based processes that are under development. So I think it's very hard to compete with petrochemical processes which have been under development for 100 years, which are fully optimized and come with something new that has a lot of benefits to offer, but maybe has not yet reached this level of refinement and full valorization as what for petroleum has been achieved. And so unfortunately, what we also see is that certain feedstocks come at a certain cost in Europe or cheaper elsewhere in the world. And so I hear a lot about companies going for their production somewhere else for feedstock cost reasons, but also for a number of other legislative barriers that exist in Europe for new processes. I know a lot is happening at the moment, and I hope that with new legislation to come, this will improve. But I think it's a difficult case. And I think for a lot of promising developments that I have seen in the past, unfortunately, in the past months and year even, companies had to stop activities, or in Europe at least. So it's something that we continuously do. I can say that for a number of things here, we will progress in follow-up projects where always companies are involved, because everything or all the projects that we do is always with company involvement and not in an advisory board, but really as an active partner for the developments. So I think there is still an interest and a willingness to do that. And also, maybe in a couple of years, the situation might be completely different. So I think we have to prepare ourselves also now to do these developments, to know where the triggers are, and what potential solutions could be, either from a legislative perspective, because that's what I heard a lot also on a workshop I recently attended with DG GROW. If there is no legislative driver, it will probably be difficult. I don't know whether that's... but that's a bit the assessment that I don't think we have to stop. We have to continue our work. And only hope that at some point also, this is something else maybe to mention, certain externalities are not included in a lot of the assessments, we do, but they are not considered by taking a decision on which route to take. And they all come now at the expense of society. So if we take those into account, that might look quite different as well. And also there, for a lot of the developments that we do, Vito is also working on that, and how can we really include and put a cost on these things, because it's also not straightforward. So that's also the kind of policy supporting work that we do in that range, and not only us, so there's a lot of others. But so that's a bit my current assessment. Yeah.
Thank you. Any last question? Yeah.
Thank you very much, Helen, for this presentation. I have a question regarding the regulatory requirements for new technologies. In the Biotechnology Act at European level, they address also the point that we need sandboxes to try to tackle the high level of requirement at European levels. Is it something also addressed at IBISBA level, or is it only technologies and then the end up for the market and the requirements at regulatory level, is it also addressed?
It's also addressed, because I think it can be a big hurdle as well. So it's new technologies, it's all the issues related to synthetic biologies and GMOs in Europe, I think, and how that is handled if it goes to the new food products and let's say the new proteins that come on the market and so on. There is a lot of the legislative aspects that have to be covered as well, and that will be there. We will have a dedicated committee even for that to look into all these things, yeah. Too important not to include, yeah. Okay.
Thank you, Hélène. If you have any other question, Hélène will be there during the break and during the lunch and during the whole day. So feel free to ask her any question about Vito or about IBISBA. Our next speaker, okay, we got a very close neighbor, and then we are going to go a little bit far now. We're going to go to Canada. With Dr. Sergei Mikhailin. He's the head of Eco-Food Lab at Food Science Department of University of Laval in Quebec City. He developed his activities in the fields of sustainable development, eco-efficiency in food processing and food service sectors, recovery of byproducts, waste management, and high voltage electrical treatments applied to the food sector. He is the author of more than 50 scientific publications in peer-reviewed journals, and additionally, Dr. Mikhailin co-chairs the Green Food Tech International Conference. So the floor is yours. And to get it? Yeah. And technology has no limit, so we're no. Oh. There you are.
Merci beaucoup. Thank you, Cécile, for this nice presentation. Well, that's my pleasure to be here, and thank you for the organizers for inviting me. So I think the first day was very exciting. And today, I'm going to cover what I was asked to cover a bit. So the eco-efficient processing innovations and how we can apply this concept to enhance the food system sustainability. But just a few words about my affiliations. So I'm coming from Canada, from Quebec City, which is the capital of Quebec province in Canada. So here you can see the campus of Laval University. So I'm professor at Food Science Department at Laval University. I'm a head of the Eco-Food Lab. As well, I'm a researcher at the INAF, so that's the Institute for Nutrition and Functional Foods. So one of the biggest Canadian institutes working on the food, health and sustainability issues. And this year, INAF celebrates its 25th anniversary. As well, I'm a member of the Dairy Research Center, Stella. So it's one of the oldest centers working on the science of milk, and it will broaden its scope to the other food matrices very soon. As well, I'm a member of the of the Gastronomic Lab, which is the joint research unit between Laval University and the Institute of Tourism and Hospitality of Quebec. So I have a lot of projects related to the eco-efficiency in this domain. So if you're interested, we can discuss this. Today I'm not going to touch this subject. And last but not least, I'm a member of the LIAN, which is the International Associated Laboratory for the Bioproduction of Natural Antimicrobials between University of Lille and Laval University. We had a very good news on the recent Green Food Tech conference, which was held in Saint-Malo last month, and which we co-chaired with my colleague and friend Rosen Ravalek, who is here, and Geneviève Gézanguiziou from the INRAE-RN. So there was a very exciting announcement of the new research network, CBOVA. So that's a research network between Canada, France, and Belgium. So if you're interested, please don't hesitate. You can talk to Rosen, who is leading the French part of this network. So also, I'm a member of the scientific committee of the Quebec's Biofood Cluster, and more precisely, I am responsible to the workshop 5, dealing with the circular economy and fight against food wastes. So just a brief overview of the INF. That's the institute at Laval University, but it is also the network of researchers from different universities and research centers like the Agriculture and Agri-Food Canada across Quebec province. So we are 127 researchers, so we have quite important private partnerships and collaborations with 25 countries. So, and in the heart of most part of the projects at INAF is sustainable food. So without any surprise, when we talk about the sustainability, we talk about the development that meet our needs without compromising the needs of our future generations. And there are some issues which we have discussed yesterday briefly. So one of them is the constantly growing population. So we do expect to have almost 10 billion people by 2050. And what does it mean to the agri-food industry? It means that there will be a drastic increase in the global food demand. So the numbers are different. But yeah, it's around 50% of increase in the global food demand, and we know that our agri-food system has different environmental impacts, so greenhouse gas emissions, land use, the biodiversity impact, and others. So we need to produce more food, but at the same time, we lose 14% of food from the production to the distribution level, and we waste as well a lot of food. So yesterday, this topic was covered also. So we need to produce more food. We waste the food, but at the same time, we see that 800 million people are affected by hunger. 2 billion have different nutrient deficiencies. And in some parts of the country, of the world, we do have the problems with the overweight and obesities, which actually brings us to the high socioeconomic costs. So how to feed the 9.7 billion people? So we can go with the conventional ways. Ooh, it goes very fast. With the expansion of conventional food production and infrastructure lines. But of course, that will be the different consequences. With the negative consequences to our environment. So the idea is to try to balance our needs and environmental impacts. So, and today we're going to focus mostly on the technologies. So what we can do on this part. And when we talk about sustainability, I think it's without surprise we talk about three pillars, economic, social, and environmental one. We can include the cultural or governance pillar, which are quite important. And in my lab and with my colleagues, we are working on the particular concept which takes into account the environmental impacts and the values of the products or services, so which is called eco-efficiency. So it is quite young concept which was introduced in 1990s but by Swiss researchers and popularized by the World Business Council for Sustainable Development in 1992. And in 2012, we do have an ISO standard, ISO 14045, which gives us the framework. So we need to define the objectives and the scope of our analysis. So then to assess the environmental impacts, the value associated with our products or services, then we need to quantify the eco-efficiency and proceed to the interpretation. Regarding the environmental impact, what is recommended by ISO 14045 is to go with the life cycle assessment, so which has its own ISO norms. So, and we can go from the resource use to the fabrication, processing, distribution, and to the end of the cycle, or to go with gate-by-gate studies. So we can estimate by this analysis quite simple categories like the energy consumption, water uptake, or to go to the more sophisticated ones, more complex ones with the greenhouse gas emissions, human health impact, or ecosystem quality. And at the end, we can estimate the different categories of the impact, so to have our impact of our products, and then we can set the goals to reduce this impact, or to compare our products with the different products in the market. Or we can estimate the hotspots where we can act at the first place to reduce the environmental impact, like in this case is the agriculture. Regarding the value assessment, here the conventional one is the economic one, so which is very important, so monetary or physical values. But when we talk about the foods, it's not enough to have only these two values. So the ISO standard gives us a broader description of the value component. We can think about the functional value or aesthetic values. For example, we have conducted the study in Quebec province regarding the relevance of announcing the eco-efficiency scores of the menus, and we have estimated if we can impact the consumer choice. And yes, the results demonstrate that yes, we do impact the consumer choice. We can really change if we announce the information regarding the, in this case it was the information about the greenhouse gas emissions, nutritional score, or the eco-efficiency score. And recently we have conducted the pan-Canadian studies regarding the information about the greenhouse gas emissions. So, and we see that sometimes we can reach up to 30% of the choice from the consumers if we announce the information about the environmental impact of the foods. So let's see some examples, and I was asked to touch more processing part and more technologies, so the new technologies. But as I told, like food service, it's one of the main directions of my studies as well. So let's see what can we do from the eco-efficiency perspective in the technological innovation level. And we can see more information about the electro-technologies, which I'm developing in my lab and in collaboration with my colleagues, more precisely with my colleague Laurent Bazinet, who is an expert in this technology, so electrodialysis, which is the electromembrane technology. So it uses the particular membranes, cation exchange or anion exchange, so they are quite selective. And of course, electro, we can think about the current. So and when we apply this current, we can actually move the ions, and we can dilute or concentrate our solutions. So what are the possible applications in the food industry? So we can think about the water purification or generalization of whey, dairy whey, so the main byproduct of the dairy industry. Regarding the concentration, we can think about the table salt production, or we can modify some products. For example, in the case of wine, you see there are some precipitates here. We can see, sometimes when drinking wine, so, and they're caused by the tartrates of potassium or calcium. So, and we can remove this by using the electrodialysis process. And what is very peculiar, very interesting, that we can install this electrodialysis model in these kind of trucks. So, and move them throughout the wineries during the season to stabilize the wine. So we can also separate some small molecules like amino acids, because basically the ion exchange membranes, they don't have the big pores. So we cannot separate larger molecules, but we can, for example, use the ultrafiltration membranes, so the electrodialysis with ultrafiltration membranes, and then we can separate, for example, peptides or larger molecules. There is a special type of the membrane in this process, which actually is a sandwich between anion exchange membrane and cation exchange membrane, and the hydrophilic layer between them. And when we apply the current, basically what we can do, we can basify or acidify our solutions. So what can be the applications? One of them is the acidification of cranberry juice. So one which is developed in the lab of my colleague Laurent Bazinet. And for example, we can produce the casein, so the main proteins of the milk. And we will focus on this application today. So how can we produce the caseins? So in milk, these proteins are quite complex. So, but the idea is that they are charged negatively, and we can remove these charges, so cut these charges, which are mostly concentrated here on the surface, by enzyme. So, and we produce the casein and glycomacropeptide. Or we can neutralize these caseins, and when we reach the isoelectric point, which is 4.6, we can precipitate them and then separate. So the second pathway is much more applied in the industry, and we can use basically the inorganic acid, lactobacteria, which will ferment the lactose and produce the lactic acid, and which will acidify our milk. Or we can use the electrodialysis with bipolar membrane. So, and that's what we have compared in terms of the eco-efficiency assessment with the inorganic acid. So, basically what we have, oops. Up, yeah, sorry. What we have done, we have compared the production of caseinate, so which is the soluble fraction of the casein. So, because the insoluble caseins has quite lower functionality, so we need to convert it to the soluble ones. So we can use the chemical acids or bases, or we can use the electrodialysis module. So here at this compartment, we can acidify our milk, and then we can use the base generated in this compartment to convert the caseins to the caseinates. So we've compared the environmental profile. So this project was done in the framework of the Research Industrial Chair, led by Laurent Bazinet, and Rosie Deschamps-Gagnon was studied the functional properties of these ingredients. So, and briefly, we have compared 4 categories of impact. So the climate change, human health, ecosystem quality, and resources. So in here we put everything on the same scale. So the worst scenario was on the 100% scale, and we see that electrodialysis with ultrafiltration, and here ultrafiltration we use not to concentrate something, is just to remove the casein fraction from the electrodialysis module to avoid the precipitation and cheese formation inside this module. So, we see that from the environmental point of view, electrodialysis had 10 unit of percentage of difference, so better than the chemical method. But of course, we see that the hotspots are mostly in the agricultural part, so in the milk production. So that's where we need to act more. But still, we have better performance with electrodialysis. Of course, when we think about the value, we should see the functionality, and we saw that from the emulsion properties or gelling properties, there were no differences between these 2 ingredients, but the foams obtained by electrodialysis were more stable, and these ingredients were less hygroscopic, and as well, with electrodialysis, we generalize our solution, and we can affect the isoelectric point of precipitations of the caseins. And what we can obtain as well is the higher amount of calcium, which is quite interesting from the nutritional point of view. But of course, the production costs, that's something which need to be evaluated, and there are ongoing studies on this point. Another technology which I'm developing in my lab is the high voltage electrical treatments, or more classical part of this technology is the pulsed electric field. So basically what we do here is we do have two electrodes, and we place our matrix between these two electrodes. And we apply quite high voltage from 0.5 up to 40 and more kilovolts. But with the very short pulses, so microseconds, or even now we can have the systems with the nanoseconds pulses. And the conventional approach is to affect the integrity of the cells. So we can impact the microorganisms, so we can destruct them to have the cold pasteurization technique, or the more innovative ways, more recent studies with the quite mild conditions of pulsed electric field can promote the growth of some microorganisms. As well, we can improve the mass transfer, so like extraction, drying, freezing. And I'm going to focus here on the tissue softening. I will give you an example of my colleague Alexei Parniakov from Elia company, which is one of the leaders on the market of the pulsed electric field systems. And Alexei presented this technology at Greenfoot Tech conference. And I think this example is quite interesting for the Belgium, because it's an example about the French fries. They use the pulsed electric field treatment to soften the potatoes after peeling and before cutting, because normally we use the hot water. So, and here the idea was to replace this hot water by the pulsed electric fields. And what they observed, they didn't conduct the life cycle assessment, but still, from the environmental point of view, with a system of 26 tons per hour and 7,700 production hours per year, we can save a lot of energy and water, so which are the evidential gains from the environmental point of view, but as well from the value point of view, we do have quite important gains in the yields. And loss of oil, because we need less oil for these French fries. It is quite obvious that the pulsed electric field treatment is better from the environmental point of view and from the value point of view. Of course, when we see the product as well, we can see some important gains. And for example, when we talk about the reduced oil uptake, so we can have some benefits from the nutritional point of view as well. But in my team, we work mostly on the innovative path of using pulsed electric field to influence the structure of the food constituents. So to impact the functionality, it's not me who work with the allergenicity, it's my colleagues from McGill University who work on them. So, and we can improve as well the interactions with other molecules. So, and the last presentation of Hélène was focused mostly on the polysaccharides. So me, I'm going to present some examples on the proteins. So that will be quite complementary. And yes, the idea was to see how we can apply it to the proteins from the whey, because it's quite a big problem of whey valorization in Canada and in Quebec. And of course, there exist different technologies of its valorization, but we wanted to see if we can target higher added value products. So we went with the enzymatic hydrolysis of whey proteins. So we do have some products on the market, of course, and it's constantly growing market as well. And when we produce the hydrolysates, of course, you all know that at the end we can have the peptides or amino acids, and peptides they have different bioactivities, antihypertensive, anti-cancer, anti-diabetic, and so on. But the problem is with the efficiency of this process, because the proteins, like the whey proteins, are quite compact, so which actually hampers the access of the enzymes to the cleavage sites. So, and the idea was, our research question was how to improve this accessibility, and we did it with the high voltage electrical treatments. So basically what we have done in the first step, we took the main protein just to understand what happens in our system. So we worked with the beta-lactoglobulin, and here we tested the classical pulse electric field treatment and more innovative one, which is the arc treatment. Here our system comprises the point plane electrode, and we can have the arc when we apply high voltages with different phenomena which occur during this treatment. And then we modified the protein, and we conducted the hydrolysis and analyzed the peptides. So we started this project with my colleagues from the University of Technology of Compiègne and with my doctoral student Roxette Agua. And quite briefly here, we didn't go with the life cycle assessment, but very important parameter when we talk about the hydrolysis is the hydrolysis degree improvement, and we compared the energy consumption with high voltage electrical treatment versus heat treatment, and we see that especially with the 1 minute treatments, the eco-efficiency scores were much way higher. But of course, I mentioned that we talk about the bioactivity, which is quite important, and we went further to identify and characterize the peptide fractions. So I don't have time to go in details, unfortunately, but some results we can see that with the high voltage electrical treatments, we have a higher number of peptides compared to the heat treatments or to the native proteins. And of course, we can play with the selectivity. So if we change the pulse electric field modes, we can play with the selectivity of generation of some bioactive peptides. And we went further on this. We collaborated with my colleague from University of Lille, Renato Foix-Devaux, who is an expert on the catalysis, and enzymatic hydrolysis, and we wanted to test the synergy between the pulse electric field, which affects our proteins and improves the enzymatic hydrolysis, and the immobilization of enzyme in order to reuse it. So how we can deal with this? And we had a PhD thesis in co-tutel of Laurie Clouseau, who has defended her thesis last month. And there were different colleagues from the University of Lille and Laval University who were involved in this project. And we were working on the second largest protein in whey, alpha-lactalbumin, and the complex protein solution, the P proteins. So I don't have time to go to the results. So if you want, of course, we can discuss them with you. And the last project, I think, is quite relevant as well for the Belgium. So the beer here is very good. We have tested yesterday. In Quebec is the case as well. And we had an explosion of the microbreweries from 50 in 2005, and now we have 350 microbreweries, and of course the major byproduct is the brewer spent grains. So, and they don't know what to do, so they can give it to animals, but they pay for it, or most part goes to the landfill. So, and what we have done here with this product is with our colleagues from Nantes, who initiated actually this project. We were comparing different scenarios from the microbreweries and brewer spent grain valorization in France and in Quebec. And Gaëlle Petit, postdoc, and now she is a professor, maître de conférence in Sciences Po Rennes. So she evaluated the different stabilization scenarios and the environmental performance of them. And we went further because BSG can be used in the human nutrition but it has a very low functionality. So we can add in some cookies or bread, but at the level of 10%. So the idea is to improve this functionality so we can extract some proteins or even go to further purification and even go further to explore the bioactive potential. So that's the project which we conduct with my colleagues Sylvie Turgeon and Rosen Ravalek, and we have 2 students. And one of the results coming from the recent study of the Jonathan is the eco-efficiency profile. Here is quite complex because we wanted to put everything together, and we compared the landfill scenario, so the basic one, the animal feed just using the flour or extracts or precipitates, which contains more proteins here, and we have estimated this kind of environmental protein content profile to have better view for the microbreweries which path we could take. So there were just a few examples how we can operationalize actually the sustainable development by using this eco-efficiency concept. Of course, there are multiple challenges which are still should be addressed. Is the multi-criteria aspect of sustainability assessment. So what we need to prioritize when we assess the environmental impact, the economical aspects, and the social, for example, which are still lacking in most part of the studies. There are some methodological issues of sustainability assessment, like the lack of the uniformity between different available tools, or data availability and transparency. And as I told, the particular challenge is considering the social aspects, which is very important. Sometimes we can give some arguments from the economical point of view or functionality or the better environmental performance, but still the technology is not applied. So because of the legislation, as we discussed, or because of the different political issues. So, with my colleagues as well from the more social sciences, we try to dig on in the current projects these topics. So I would like to thank you for your attention. If you have some questions, of course, we can discuss and you can visit the website of my lab. And I would like to invite you to the next edition of the Green Food Tech Conference, where we discuss all these topics regarding to sustainability in the food processing, and more we go to the consumer level. And the last slide, I would like to invite you to the larger conference organized by INAF, is the Benefit Conference, which will be held in Quebec City this November. Thank you for your attention.
Thank you very much. And I would like to thank you as well, because I had the opportunity 2 years ago to follow a conference which was, the beginning was quite the same with Jan Kovici, very difficult to listen to the situation, but your happy handing with sustainable French fries is just wonderful. So thank you. Is there any question? Yeah.
Thanks so much for the great presentation. Really, really interesting, and I loved some of the examples that you presented. So my question was on environmental impact assessment, and specifically how you quantified human health effects and ecosystem quality effects. Because from my perspective, let's say that analyzing midpoint impacts is relatively straightforward, in quotes, obviously provided that data is available, etc. But analyzing endpoint impacts is very, very challenging and also carries high uncertainties. So I wanted to get a sense of how you did that, what kind of data you used, what indicators you considered.
Yes, we are, and I agree, there are a lot of methodological issues in this part. We use the impact, I think, for the example I've presented, 2000 plus, so where they combine some midpoint categories in the human health impact categories, and ecosystem quality is the same. So we didn't go deeper in these methodological things, so we used the database EcoInvent in this case, and we completed with the industrial data and the literature data. So we didn't dig up into the methodological issues, but...
No, it makes sense. I think it's very important to communicate the uncertainty about that because, these are pre-made databases that are quite limited. But for the rest, really, congrats. It's amazing work.
I totally agree with this, yeah.
Any other question? Yeah.
Hi, thank you very much. It was a great presentation. I was wondering on the whole, on the aspects of the energy use. I think Quebec is using a lot of hydroelectricity. Is that included in the methodology to assess?
Yes, actually, for the Kaizen part, we have done the sensitivity test. So we were imagining to move this process to different countries with the different electricity mixes. Even in Canada, if we move to Alberta, for example, it's not the case, so they don't use hydroelectricity. So it's, I think, the fuel oil. So, and the conclusions, the main conclusions were the same. So electrodialysis performed better, but I totally agree we need to consider this, because when we talk about the electricity, so yeah, sometimes we don't think where it comes from for electric cars, for example. And sometimes the sources are quite impactful, like the coal, for example, yeah.
Okay, thank you.
So what we considered in the first study, but not, for example, for French fries, they didn't do the life cycle assessment, so that should be done.
Yeah, okay. I'll talk to you later about Spain grain. I'm interested in that.
Oh yeah, sure.
Yes. A last question? No? Then thank you very much.
Thank you.
And so the last presentation before a break is going to be made by my colleague, Julie. I told you that we had a project with Circular Wallonia. She's going to speak a little bit more about it. Julie joined the team about a year and a half ago. She's project officer with a background in bioscience, engineering and food science technology. And she's here to bring a more scientific perspective of the project. So the floor is yours.
Thank you, Cécile, for this presentation. I'm pleased to be here with you guys to talk about circularity, to talk about CleanTech, and more specifically about this one project on which me and my colleague Cécile and I are working, which is the Walloon project on food byproduct valorization. So in a few words, the Walloon project has the aim of putting up a proof of concept for the valorization of 4 types of byproducts that are issued from the Walloon agri-food system. And all of that through one mutualizable process. So during the first phase of this project, 4 byproducts were identified as products with a potential of valorization because produced in significant amount in the Walloon agri-food system. So these byproducts were canola meal, wheat bran, spent grains, brewer spent grains, and apple pomace. So the idea here of this project is to not only look at the technological aspect of valorization, but really to try and develop a new value chain for the valorization of byproducts and really to have a 360 vision of this entire value chain. So as I said, obviously we are working, doesn't work, but on the stabilization and valorization process of these byproducts, but also working on opportunity analysis, which was done before with the the analysis of which byproduct that we should be working on, working about technical feasibility. We talked about it, Sergio talked about it, about eco-efficiency. What is possible today, it's great to have research, but it also has to be feasible at an industrial level. So here we're more working on not only on the research part, but really trying to focus and to work towards more of the market and industrial phase, which is why we're also conducting market analysis to develop products that are adapted to the market needs and market demand. And finally, doing a financial analysis because, as mentioned before by Hélène, in the question that was asked in the public, a lot of research is done, but how is it actually feasible at an industrial level, especially financially? So we've seen it before with these two presentations. When talking about byproduct valorization, it's a very wide spectrum. So it's like talking about food industry in general. There are so many processes that can be chosen, so many technologies. So we had to set criteria to choose one process that we decided to use. So these are one of the few criteria that we put to ourselves, which were both opportunities but also constraints. So first of all, obviously sustainability. The goal of valorizing byproducts is to stay in a circular and sustainability mindset and not to pollute or create more byproduct. We also wanted to have a process that is as mutualizable as possible. In Wallonia, there are a lot of byproducts that are produced, but in very dislocated in small quantities that cannot be valorized independently. So coming up with one that could be adapted to all these 4 byproducts. Also, the financial viability of this process, and finally, the state of the art. As I mentioned, the goal of this project was really to push the proof of concept more towards a proof of concept in the market in industrial phase and not staying at a research phase. So finally, this is the valorization process that we decided to go with. So when talking about for the apple pomace and beer spent grains, brewer spent grains, there are obviously wet matters that need to be stabilized before. So we decided to go through with drying with a pressing step to eliminate as much water as possible to reduce the economical and the financial and sustainable impact of the drying step. For the canola meal, which are still very concentrated in oil, about 15 to 20% of oil remaining in them, we are going through it in oil extraction, solvent extraction. And finally, the main real step of valorization and transformation innovation in this process is the last part, so the milling and the classifying, which is done by air classification. So what is air classification? Just to mention, the pressing and the drying and the oil extraction was realized, tests were realized by the Syllabor, which some of you will have the opportunity to visit tomorrow. And the last 2 parts, the milling and the classifying part, are currently being done at the Terra Center, which we will also have the opportunity to visit tomorrow. So a bit more about air classification. It is a sustainable method for protein concentration today that is used a lot. It is based on the separation of flours based on their sizes and their particle mass. So today it is used a lot in non-biomaterial processes, but also for the extraction of protein from pea proteins or faba protein, etc. So this technology, as it is a dry technology, it has the advantage of allowing to not use any toxic solvent or chemicals. Therefore, no need either to have post-treatment extraction, so no exposition to heat either during evaporation of the solvents, which makes it overall a bit more sustainable than the typical solvent extraction that is usually used for protein concentration and protein isolates. They also have a bit of chemical advantages, as this technology allows to conserve the native state of the proteins that we want to extract. So with this technology, we will be able to have 2 flours from the byproducts that we are considering, one that is enriched in protein. So I'll just have a short video to showcase this type of technology. So as you see, it really would allow to have two types of fraction from the flowers that we would obtain from the 4 byproducts that we're using, one enriched in protein and one enriched in fiber, except for the apple pomace. Obviously, that has no protein, but we're working to see if it would maybe allow us to have one fraction enriched in pectine. So that is basically where we are at now. We are working on that with the Terra Center at Jean Blou. As I mentioned, the goal is to really have a 360 vision, so we also have partners, working on logistical analysis, financial analysis. We're also going to be doing, tests, recipe tests, and functional, techno-functional and nutritional analysis to really try and meet the market demand as much as possible. And so just to conclude, the idea here is really to have a valorization process of these 4 byproducts while staying as sustainable as possible, as well as financially viable, which is crucial today. So thank you, and if you have any questions, don't hesitate to ask questions now or later.
Thank you. Is there any question? Otherwise, we can just take the question during the break as well, because I think that the morning was already quite heavy with a lot of information, so don't hesitate. Is there no question or during the break or no question? Okay. Then we are going to make a 30-minute break. If just during the break you are going to have the opportunity to taste different biscuit made from byproducts. So I'm not going to tell which one are made by byproducts, and we are going to discuss it after the break. Thank you.